So our next class of tools are systems. And systems are types of abstractions, but they don't just simplify the underlying reality, they capture the way that the parts interact to form a whole. So where an abstraction is just kind of like a flat, motionless, static image of reality, a system is an abstraction that also captures the way the pieces are interacting with one another to do something that's more than just the motionless pieces by themselves. So there are a couple different ways we can look at systems and learn something about reality. But one thing we have to keep in mind is that there are systems on so many different levels. Like every part can be thought of as its own whole, and every whole is composed of parts. So, I mean, you've got atoms, which are these subatomic particles that are all moving around and, interacting with one another. And then they can form molecules, which are systems of their own. Molecules can form bigger systems like a neuron, uh, which is clearly, composed of lots, billions, if not trillions, of molecules. And a neuron can form a piece in the whole that is a brain, which is clearly a system of its own, and that can just be a single part in an even larger system, which is an economy. So you got to keep in mind that there are systems on all these different levels. And once you start to think about that, we can start to ask ourselves, how are these systems the same and how are they different? And start to classify different systems into different categories. And a couple different categories that I found really helpful are, first, the difference between a linear system and a nonlinear system. So, without worrying too much about the mathematics, a linear system is one where the order of the inputs into the system doesn't matter. So if you imagine that you're standing on a grid and I yell out to you, move north 3 feet, east 7 feet, south 2 feet, west 1 foot, north 8, south 2, west 4, whatever. It doesn't matter what order I give you those inputs in. You'll always end up in the same exact spot. Another system that's linear would be like water pipes. It doesn't matter which water molecule comes next because we assume they're all the same. So it's really easy to simplify linear systems, and humans are really good at designing and manipulating linear systems. We got assembly lines where you just assume every part is the same, so you don't have to worry about which one comes next. You just plug it in, and you can make really long chains of these that produce complicated results, but they're still linear systems. And those are fundamentally different than nonlinear systems, which those are where the order of the inputs matters a lot. So human bodies, for instance, are nonlinear systems. It matters a lot what order we eat food in. So like if you gathered all the food and water you need to survive for a month, it matters a lot what order you eat those in. If you drank all your water before you ate any of your food, you would die. You would either die of water poisoning, or starve to death. Other things like this are ecosystems where it's tough to model nonlinear systems because we don't all the parts are interacting and influencing one another in ridiculously complicated ways. Weather is another one. You still can't predict the weather very well, and that's because it's a nonlinear system. Much to the dismay of economists, economies are highly nonlinear, and as much as they think they can predict them and stimulate them, it's just these are nonlinear systems that you cannot understand in the same way you can understand a linear system. And I'll go on to a different one in a second.